discuss why our presentations are in the political stream or session. So I'm hoping they're not too technical for a lot of people in the room. Probably stay close to the microphone. So yes, I changed the title a bit to link open geodata for agriculture because basically for my project, my interest is very much in how these things come together. So the GIS science world and the linked data world, and how to apply for agriculture because I'm working at the Wageningen University. So and also in the Wageningen environmental research group. So we do a lot with agricultural research. So my presentation is a little bit less technical. I'll try to make it a little less. Last night I tried to make it a little bit less technical actually. And what I wanted to present is a bit of like lessons learned from a number of EU projects that I was involved in from the last couple of years. So some of the names might be familiar to you. I'm mentioning ACLID. So I have a few words on the ICASA master variable list actually. But I just had quite a few questions. Basically the only thing the Geo4Web was not a non-EU project. It was a very small project in the context of linked data and GIS, just spatial data. It was very interesting. So this was my idea for the situation. I have like 4 of these key points or key problems that I saw like surfacing in all these projects, and a lot of them I was happy to learn are also mentioned yesterday. Were also mentioned yesterday and a little bit this morning, but I heard a few solutions actually, so that was quite good. Some of it also probably shows the like history and the speed of development in these areas. Because this was an idea from the Liège project. At some point we had Liège is like the also like a platform where for integrated assessment and sustainability studies on a European scale. We try to collect all the different bits of knowledge about models and data sources and policy decisions and all that kind of stuff, and put it into a system so that decision makers and scientists could quickly find the necessary resources. And of course, the typical way to do it is to take like a content management system and start tagging all the different bits of information that you put in with keywords, and then by using these keywords, you can do the faceted search and relate information to each other. And then as a small side project within this Liège project, I kind of got some funding to look at linked data, because that's the obvious, at that point was the obvious next solution and a better solution to do the kind of stuff they wanted to do. And I came up with this like at that point revolutionary idea that like a decision maker could make use of an app and just use natural text to answer his question for research or that answer his question about which model to use for a certain air pollution study in a certain region. And then at the back end, the system magically would use all the linked data to find the answer, so to find the best suitable model, and also could provide links to the possible input data to run the model. But that was kind of too far-fetched. So basically the idea is that we have is that using this linked data, you can teach computers to do very interesting things. So there was an example of that. But then the problem I ran into is that it's actually pretty difficult to do it. And the users are very critical. So all the users of software now are very much used to things like Google and Facebook. And what goes behind in these big organizations, what they can do, it's very hard to compete with that in a small research project. So basically, whenever you come up with some kind of search mechanism, you have to compare with Google. So it has to be as smart as Google search, basically. Otherwise, people think that what you implement is bad. And in particular for the EA's project, because it was a few years back, and the technology was not that good as it is at the moment, we found out that it was more practical to keep like the scientists in the loop, so the mapping wasn't fully automated between the resources, but there was like a decision table at some point that the researchers could fill in and manually control the mapping. So the outcome was, they trusted more, had more trust in the outcome, actually. So we needed to make it was promoted as a very magical system, like in the background all this magical stuff was happening in the linking, but we had to make it less magical to get enough trust so people would actually use it. And then for each point I have some considerations. So these are like open questions maybe. I think it's as computer science at that point we didn't have enough knowledge about how to deal with this. Go into more incomplete and data sets are big data sets are you have a lot of unknown values probably, and the quality you're probably not sure about quality. There's data that's beyond your control, so you have to at some point deal with all these missing data values and less accuracy. They you don't exactly know what it is. And how to deal that in the software, that was also a question from Paul in his keynote. But we have to, as computer scientists, I think we still have to learn how to do that. And probably the linked data world is still has a bit more control than if you go to machine learning, because then you get this big maze of numbers and you have to the computer figures out what the relationship between the numbers is. The next point I like very much is also a very interesting thing. If you come from the GIS world, so it's we have these two assumptions: the closed world and the open world assumption. So the GIS world is more like a closed world approach. So we think that everything we have in the data set is basically the truth. So we don't have the statements in the data set, then we assume that that's false. And the open world assumption is more like the linked data world, so everybody has a little piece of knowledge and we bring it together to get a complete picture. So that's the key thinking behind the two worlds that is different, and at some point we have to bring that together. And then currently I think it's very important as computer scientists, you work in this world, you have to invest in things like natural language processing and see where the machine learning thing is going. And if you want to do natural language processing in the agricultural domain, it helps to have like a domain-specific focus. So you know the specific words that are in terms that are relevant to the agricultural domain and use those for your language processing. And then the question about the missing user. So how to sell all this magical stuff and linked data and fancy use of geodata to be used in that. So I think the question if you actually have to do that or you just use all this stuff behind the scene to make more intelligent and smarter software, and they just use it, take the benefit. So that was the first. Second thing, and this goes back to the using linked data for big spatial data sets. So I've learned that I have to use Virtuoso for that. But here in this is the Samagrove project, which in which we looked at the scalability of big data architectures and how to use that for spatial data in the agricultural domain. And it was about federated triple stores, so running Spark queries over federated spatial Spark queries actually over federated data sources and try to reach a certain level of performance with it and make it user-friendly. So we had this like a search interface, which was rather technical, which could select a time period and a spatial region, and then the system would run and find data sets in that region. And then from these data sets, you could make a selection and retrieve the data in a format you could select. So that was the idea, but it was a research project, so we had very limited hardware to run this on. So we actually ran into a series of performance problems with this. And it was also the case that we wanted to study big data, scalability and big data applications. So the people at the data center were really asking us to push the system, and most of the data they got was like million triples. So that was they said, oh, that's too easy. You have to give us really big data. So we gave them NetCDF climate data files of worldwide scale, and said, okay, go ahead and triplify that one. So these NetCDF files are like 100 or 120 megabytes in size. And if you start triplifying all the cells, it's basically a stupid thing to do, but if you want big data, then that's a nice experiment. And the data explodes so that for these 100 megabytes of NetCDF data, you would end up in having gigatriples of gigatriples to store in a triple store. And that's just one file, and we had like hundreds of those files. So that actually broke the system because it was too much data to handle. So we had to scale down the practical use. So in the end, you could make a selection like half of the Netherlands. Netherlands isn't too big, so that would be the maximum that the system would be able to handle. So you could select some data, some climate data, and the system will make this selection and return this selection in triples, and the triples will be converted back into NetCDF files if that's what you want. So it was quite an interesting experiment. Unfortunately, we just had to scale back the capabilities of the system, so the region that people could select. And then, of course, we have a lot of geoscientists in our organization that we asked to test the system, and they use the GIS system. So they said, okay, working with NetCDF files, we do that daily, and there's a simple Unix command to select the region out of these files. So why all this hassle and all the promotion of big data and triple stores, and saying that it's very fancy and can do everything, but in practical sense, it didn't make any sense to them to go through this whole exercise. So they kind of lost trust in all the technology they were trying to promote as a nice solution, but it's more like a nice solution in the future, and people don't necessarily see that way. So they prefer to stick to traditional GIS systems and NetCDF for workflow. So the lesson here is from this project actually we had to find a nice mix of a practical, usable mix of GIS engines, let's say, and triple stores, so like the big data side, the link data side, and combine them so do part of the spatial searching in the GIS system, and then use that result and connect it to the link data, the triple stores, and use both to retrieve the data or do spatial operations on it. So it's more on the finding a practical solution. And I think now these days you see that the vendors of triple stores are kind of doing the same thing. So they take the open source GIS technology and including them into the triple stores to solve the same thing that we were doing with using separate systems at that moment. So yeah, these are the story about the exploding data sets. There's also this thing about geoinformation data sets that not often are very precise. So it's one thing to refer to geonames, for example, like a mountain range that has a name, but it's not a precise geometric structure or like polygon in the geoinformation data set. So it makes it more difficult to refer to it. And internally we have this geodesk that supplies all the geoinformation to all the research organizations. And a lot of these people still just think in maps. So that is also how they produce the data sets. So if you get a geoinformation data set, it might be very map oriented, and you still have to do some processing on it to make it actually usable in a non-map fashion. And the last point I covered that. Even more, probably won't go into that, much more details. So I think it's kind of the spatial thinking part is that we do a lot with geoinformation, so there's definitely value in the relationship of objects. If they're next to each other, they might be more related to each other, and those kind of things. Also, you have to represent those in link data if you start moving from geodata to link data. And these, I have on the slide, I think. And what we also learned is, the geodata sets, we have this group of experts that work with it, and they're very bad at filling in metadata. Some recognition there, I guess. So in the end, you still have to go back to these experts and ask them, okay, what is the data and what's the accuracy of it and what's the precision and which projection or which spatial projection are you actually using for your data set. So even though we have Inspire and the nice fields and you can fill it all in, but it's not often that it's actually being done. Especially if the data set in origin is a very internally oriented resource, so they don't think about publishing it on the internet and everybody access it. And then I think this is also like an interesting discussion. There are already like 20 or 30 years of geospatial standards in existence, and we have these spatial data infrastructure, so a lot of things already have been solved in this world. And now with linked data, we're trying to redo everything again. So there's definitely some, depending on with whom you talk, there's definitely some conflict there that has to be solved, I think. Or maybe not solved, but find a way to work together better. Third example, and here is actually some code, since I'm a computer scientist and I learned how to have some code in my slides. This is kind of the same thing that these two worlds that we're talking about now, like the geo professionals and the linked data professionals, and that both excellent groups, of course, excellent communities with specific knowledge. But there's also an outside world, like simple web developers who don't speak either language. So we have to. This is quite simple. We have to like translate what we are doing basically into something that the other group, the outside world, should be able to use very easily. So we have to invest in very usable APIs to get to the spatial data, to get to link data, and like Thomas showed, the performance is really important if you build something on top of such an API and it has to be a mobile application. You don't want your users to wait for more than 5 seconds before the data shows up, so performance is really critical point in that. This is also about the different worlds, like the semantic web technology is not really built for spatial queries at the moment, so there's no, you have to run to GeoSparkle. I guess that's the basic thing to use at the moment if you want to do like overlays of data or find out which point is next to or a certain distance to another point, or which two polygons, spatial polygons overlap. There's no other way, I think, than GeoSparkle. Maybe there's another Sparkle ST or ST Sparkle. So there are like two standards, but GeoSparkle is definitely the way to go at the moment. But it's an OGC standard, so it's very inside the GIS world, and it's a very big standard. So there's, and the other, the other choice at this point is the W3C standard, which currently only defines like a spatial point. So there's nothing else, there's no lightweight standard to use. There's no real option other than investing in learning GeoSpark and figuring out how this all works. And then still there are issues of performance, I think. And definitely we are researching all these linked geospatial data things. But you can discuss what is in an operational stage at the moment, or what still needs, what still has rough edges and is difficult to use, or if you use it, then you're not really sure if it still would work in a year's time. There's also this interesting distinction between using vector data and raster data. So there's two different types of spatial data sets. One, like vector data, is ideally suitable for translating into link data, because you actually have points and lines and objects. Raster data is more like remote sensing data, so images, and you have these cells which do not translate very well into link data at the moment. But raster data is mostly, if you look at big data processing, like Paul said, they focus on like raster data, arrays of raw data and numbers, and that's why you train your machine learning algorithms on. And it's not so much the vector data. So there's like an interesting difference in these two data sets and how we are going to use them if we actually move to big data and data analytics. And like Johannes said, this was very interesting. I also said it at one point. Johannes said it before dinner. Maybe we should talk more like link data with a small n and a small d, so no capitals, and then more focus on these standards like JSON-LD and GeoJSON, which are much more lightweight ways to approach them. There are many more developers that understand how to work with that, much more than people that actually know how to work with RDF and GeoSparkle or WFS and WMS. Well, WMS is pretty simple, but WFS becomes much more complex. Okay, fine, this is the final one. I'm not bored yet. This is actually the ACNIP project, the ICASA. What we learned there is it takes a lot of effort to come to these shared definitions and semantics. ICASA or ACNIP is like an intercomparison of crop models, let's say. So worldwide, there are just a limited number of crop models, like 27 or so. And ACNIP tried to come up with a way so that you could run all the crop models for a certain site, and then do like an ensemble run and combine the results to produce like a more reliable output and prediction of these areas. But then all of these models have different inputs, of course. So at some point you have to combine all the data you have into some common format and provide some additional. So the common format would be the inputs that are shared by all the crop models, and then you have to provide some extra information, so the specific extra information per crop model, and you could use that data set to run each of the models, and each of the models produce some output, and there was like a common denominator in the outputs, like the yield and the very basic numbers that each crop model produces, and store those in the database again. So we had like a number of scientists. I think it already scaled down to like 10 crop models, I guess, that we worked with. Maybe even less. But we had a lot of discussion about the scientists that developed these models, about the shared definitions and semantics to be used for this harmonized data storage. And of course, linked data was a consideration in that project, but in the end, we used these CASA master variable list, which is kind of like a traditional list of all, like 400, I guess, of the most used variables for agricultural field trials. So you get the nice acronym of the variable name, and the units are defined with some description. And then we use that as the key list for this harmonized data set, instead of all the fancy linked data stuff. But it was just too complicated to introduce that into the project. And it's just, the CASA variable list was something that already existed, so it was quite easier to just take that and have everybody try to have everybody conform to that list, instead of starting all the discussion to come up with something new. So it definitely saved, in this project, definitely saved a lot of time. But yeah, you end up with something like this common denominator thing. And in the end, somebody has to, it's nice that you have all these discussions, but somebody has to implement something. Usually it's a software guy who has to make some practical decisions at some point. But yeah, like Johanna said, we definitely have to promote reuse and standardization for ontologies. I think that's really lacking at the moment. Many people get to start an ontology from fresh, and then somebody has to do a mapping between ontologies. It will be like a hell of a job at some point. So in the end, if we don't like start sharing ontologies, we have some very complex linked data to process. So hopefully you can stop that from happening. The existing standards, AgriBlock and GACS I mentioned, are very important, even though they're thesaurary, but still it helps if we all use those. And the thing I ran into, which is very important, is like this ontology of units. Units of measure would be very sensible to have and start using the same one. And definitely, if you get a data set from a scientist, the first thing to look for is how do they define their units, and are they even defined in their data set? Because conceptions about units or misinterpretations of units are a very big source of errors, I guess, in models, software. So definitely helpful if we find one and all start using that. Another interesting example I ran into recently is that if you want to use create linked data for weather, meteor data from weather stations, it's pretty difficult to find an ontology for that. While I would think that it's so common, everybody knows temperature and rainfall, all the basic variables that we want to use, but there's no single ontology for that everybody is using. And so that to me would be like, if you start somewhere, that would be a good starting point to have an ontology for that we all use. The interesting thing here is that what I've learned is that there's a lot of history in meteorology organizations in sharing data. They have these systems already by sending text messages to other people, other public institutes to share the data. So they are kind of burdened by all the existing systems. Don't really want to invest in all these. Well, the investment in new technology like linked data is rather slow, I think. And also they have like a commercial interest in not make the data too open, I think. So that really kind of stops them from publishing all the data as linked data. So right now, KNMI, which is the Dutch, the official Dutch meteorological agency, if you want the data, they have daily weather data available, but you have to go to the site and use FTP to download the data set and then onto your own computer and you use it, but you download it like a comma separated file of values, so definitely have to know what's in there as well. And that were basically my 4 points. I had many more, but I tried to cut it down to something manageable. So I'm sure you have many questions.
Thank you, Rob.